Lecture 17, Scheduling Algorithm Evaluation and Unix and Windows. Okay, so in the first part of this topic, right, we're going to talk about evaluating what algorithm we would like to use. In some cases, and arguably like a real-time system is one of them, it's pretty clear what we would like to use and why. There's not too many choices to be made. There's like not as much trade-off as there would be in certain other circumstances. That's fine, right? But in many cases, it's not immediately obvious what makes the most sense, what gives the best overall performance, assuming that you care about performance. And we've talked about a number of different criteria and why those different criteria matter, and accordingly we can consider carefully which of those criteria are the ones that we want to focus on, and all of those things will eventually lead us to presumably choosing something, right? But I mean, yeah, we need a definition of what is best. Like, what is the best overall performance implies that we have an agreement on what does it mean for this to be the best. And let's assume that we have one. I'm not going to say what it is, right? Every system has its needs. Some of them are more focused on fairness, and some of them are more focused on other things. And that's okay, right? Like, whichever one you choose is not wrong. It's just I'm not going to sit here and say, yes, I know for sure that this one is definitely the best, because I don't know the system that you're building and I don't know the application for it. But let's assume that we have one, however it's decided, right? And then we need to evaluate somehow a given scheduling algorithm to see how well does it meet the criteria that we have defined. Sounds okay, right? And we've discussed some level of evaluation where we've talked about like a little bit of the details of some of these things that we said some algorithms don't care about fairness and others don't care about priorities, and that might be acceptable, right? But a theoretical discussion where we think A is better than B but worse than C is maybe not the most scientific approach, right? What do we do in science? We do an experiment and we gather results, and then we learn something ideally from what we've done, and that would be the ideal case, right? Can we actually evaluate this, and based on our evaluation, hopefully we learn something. So we make a decision using it. Okay. So given that we don't have a specific criteria, right, what I want to focus on is how to decide, not evaluating a given scheduling algorithm according to specific criteria, because again, I don't know what system we are talking about, and there's no perfect, ideal, everything, one size fits all solution. So we're going to talk about how to decide rather than talk you through an actual decision. Okay, option one, deterministic modeling. And deterministic modeling looks a lot like writing test scenarios for a lab project, or maybe test scenarios for code that you write on a co-op term, something like that. The test scenario has inputs, it has outputs, and we can evaluate the outputs to check for correctness as well as performance. Why do I say check for correctness, right? This isn't unit testing in the typical sense. It's not, but I say correctness because usually we want to at least imagine that the algorithm we're talking about is correct in its implementation, but evaluation of correctness in the sense means that like processes don't starve, right? Response times are within a certain window. Those sorts of things are what I'm talking about when I say correctness in this context, as opposed to like it doesn't crash or tasks don't get forgotten about, either of which would be bad, but that's not the thing that I want to focus on in this case. And so it looks to some extent kind of like a unit test, right? So a simple test case does something like this. Right, we say all 5 processes arrive at time 0 in this order, and given these processes and these burst times, we run the target algorithms. And we get some answers, right? The source here will say something like, first come, first serve results in an average wait time of 28 time units, and shortest job first results in an average wait of 13. Round robin with a time slice of 10 time units has a waiting time of 23. Okay, in all cases, the total execution time is the same. There's no avoiding the work to be done, but the waiting time is different. And if we've decided that waiting time is important, how long do we wait before a task gets started? Even though, yeah, it potentially does still take a while for it to finish. If that's the thing that we care about, well then, we have an answer, right? We have a test case, and given different modeling, we will maybe get different answers. It really just depends on which are the test cases that we run and how many of them, and how, to a certain extent, lucky or unlucky we are sometimes when we execute these test cases. But okay, that sort of thing is not going to cover everything, right? It's a start, but it's not everything. A more precise version of the evaluation would assign some sort of penalty to the process switch, which would make it a little bit more realistic. First come, first serve, and shortest job first each have 4 context switches, and that results in no extra switches because they don't switch between tasks during the run. But round robin will have 7 context switches, so it's fair to say actually that with round robin the total execution time will be higher because more time is spent switching between the different processes, and that kind of makes sense, right? Like when we are handling these interrupts, when we are handling the regular process switches, we expect that takes non-zero time. It may not be relevant. It might be so small that we just don't really care. But for a more accurate model, we can choose to include it. And so, yeah, test cases that begin to look sort of more realistic will obviously not have everything as statically initialized and just standing around waiting. I mean, that's fun and it's easy to do as a test case, but real life is not quite like that. In fact, what you probably want for a more realistic outcome is something that's more like a simulation, right? So it includes tasks that arrive but not at the start. It involves tasks that arrive after some time has passed. It involves periods where the idle task runs. Those sorts of things are all possible using more detailed simulation. Deterministic modeling still has its place because we do want effectively sort of unit tests. We do like the idea of being able to have reproducible results, so that we just run this test repeatedly and validate that we didn't break anything or that nothing has changed unexpectedly. That's nice. But reality isn't always as nice. So what we actually want is some level of determinism and some level of randomness, right? So real systems have randomness in them. They require that we recognize when the time that the user requests something is from the point of the computer random, right? There's ways of modeling like when we think stuff is going to happen. But there is absolutely no guarantee that it will happen on this regular schedule, and even for situations that we've talked about where we have periodic tasks, we've been forced to acknowledge that aperiodic and sporadic tasks do exist, which means that sometimes we have to drop what we're doing and deal with something that turns out to be more urgent, or deal with something that is unexpected, and that's just the name of the game. Here's a thought, right? How does randomness work? Well, randomness is hard to reason about, right? It may be the case that most people log into a server at the start of their workday, but everybody's start of the workday is a little bit different. Even if you're supposed to start at 9, right? Some people get there early. Some people are a little late today because there was a crash on the highway. Somebody has been at their desk, but they didn't actually log into their computer because when they were there, they got interrupted by a colleague who wanted to ask them a question. And even though it's relatively predictable, everybody who's coming to work today is going to log in at around this time, the exact time is, from the point of view of the computer, kind of not predictable, right? But it's also not totally random. It's not, it could happen at any time because, it's much more likely that people log in at the start of the workday as opposed to people log in, at 2 o'clock in the morning. It's not to say that never happens, and one may easily imagine there are lots of scenarios where, the server is down and somebody has to log in the middle of the night, but that's complicated. Okay, so this leads us to queuing theory. And queuing theory is, as the saying goes, literally the theory of queues. What makes queues appear, how they will behave, and how do we make them go away? There does exist in queuing theory a kind of modeling that we're looking for where we can treat arrivals of new things to do as random and have a mathematical distribution for how we expect things to execute. And using those mathematical models, we can reason about what we think is going to happen, even in a system that has a significant degree of randomness to it. Thing is, the problem with queuing theory analysis is it's mathematically complex and it's not suitable for every kind of scheduling algorithm because we're just not going to be able to drop everything we're doing and do this long, difficult calculation as we need while we're trying to schedule the next task to run. So queuing theory is, I'm going to say, too advanced for this course. Queuing theory will get mentioned as a graduate level topic, but somehow hints of it find their way into courses like, ECE 459. So we'll leave it here for now. Whatever we do, if we have a simulation, a deterministic or statistical sort of modeling, the simulation will account for more things like clock interrupts and switch times. And it's possible to do an all-software simulation if you want. This can be a little more difficult when you're trying to make it run for you're simulating an embedded system, which is not exactly the same as the laptop that you're running it on, but it is within the realm of possibility. And the thing about a simulation, of course, is that a simulation is only as accurate as you make it. You get to choose effectively how detailed you want it to be, and you can invest a lot of time in it, and it will give you a more precise result. It is an engineering decision to come up with, where's the line? How detailed does it need to be? Before you're just wasting your time getting sort of extra precision that doesn't matter because you don't need it to make a decision or you don't need it to accomplish the goal. And your system may come with an emulator. If you already are working on an embedded system and the embedded system comes with an emulator, that could actually save you a tremendous amount of time because then you don't have to write something like this yourself. You don't have to simulate how long does it take for instructions to execute on the hardware. You have an emulator whose purpose it is to show that sort of thing and to execute that. So those are nice, but the problem is that they're not perfect either. And you may have encountered the situation where you're not sure when you encounter a bug, whether the bug is in your code or whether the bug is in the emulator. And you can run it on the actual hardware and try to see what happens, and maybe you prove that there's a bug in the emulator. That's pretty good. But yeah, the emulator is great, and you can use an existing one, but it may not exist. So simulations, just as anything, can only tell us so much about the actual performance of a scheduling algorithm because the simulation is based on assumptions, and those assumptions include things like what is the user behavior, but also includes assumptions about what hardware are we going to use and how does that work, and that's not always accurate, right? A general purpose operating system has to work to an acceptable level on basically any hardware configuration. They can set a minimum and they can say, well, it needs to be at least this many megahertz or this many gigabytes of RAM or something like that. But the exact precise hardware is difficult to predict because we don't really know what the user is going to buy. But actually, on this subject, let's take some time to consider actually some of the algorithms used in commercial desktop and server operating systems, specifically Unix, Windows, and Linux. I'm not saying that any of these operating systems have everything right and that their form of scheduling is optimal. Optimality is hard to define, and again, it's a question of like what is the goal that we're trying to accomplish. But I mean, they must be doing something right, because if their choices were awful, then like user or customer pressure would surely force them to change something, would it not? So let's talk about that.